Now, let's try to understand the detailed mechanism in terms of pricing discrete time based derivative securities. Any derivative security, if I have to find the price of it in a discrete time, what is the kind of mechanism that I am going to follow? So initially here, I need to understand a few important terms which can help me effectively do the pricing part. So a few basic concepts. One, we have to talk about what is meant by filtration. Filtration typically represented by Ft for any process. When I am saying the filtration Ft for any process, let's say for the stock price process, if I am saying Ft is the filtration for a stock price process Su, which is U zero, U lies between 0 and T, is nothing but I have the history of that process, I have the history of stock prices up to time T. Right, when I'm saying Ft means I know the value of all the stock prices. I have the history of all the stock prices up to time T. Right, all the information, whatever is there with respect to the stock prices up to time T from 0 is known. So when I'm saying some particular process, the share price process is Ft measurable, right? Filtration is basically the knowing of the information up to time T. So when I say that some kind of a stock price process St, if I say it is Ft measurable, then once I know all the history of this particular stock price up to time T, once I know Ft, we know all the values of Su where U is less than or equal to T. Up to time T, I know all the stock prices. If I am saying the stock price St is Ft measurable, it is given that once I have the Ft, which means the history of all the share price process up to time T, then I know the share prices up to time T, then we are saying this is Ft measurable, right? Now, on this context, we have a slightly different definition which is called as a previsible process. What is this previsible process? If that particular process is, if any process is Ft minus measurable, it's not Ft measurable, Ft minus measurable, which means the process is known pre-visible, it is known beforehand, it is known based on all the information up to T minus. So it is known based on I would be able to know this process based on all the information up to time T but not including the time T. Mean I know the information about this particular company, let's say from SU to S15, but I don't know S16 up to time T but not including T. And in many cases, especially when we are building a replicating portfolio, this is what is the major activity that we are going to do as a part of the pricing. When we are building a replicating portfolio, we will very well establish that phi t is a previsible process, which is the number of units that I have to number of units of share that I am typically purchasing at time T, where the stock price is St. And we also talk about psi t, amount of cash right, where we are typically investing at time t. All these things, these will become two major previsible processes, because just by knowing the value of the share up to time t, I am thinking how much I should hold at this moment based on the information up to t but does not include the time t. That is where we are calling these two are a part of the pre-visible processes, because I am making my decision now based on all the information about the stock up to the time period t but does not include the period t. So whenever we are using this mechanism, we will be building a replicating portfolio, right, as a part of the derivative pricing. Or before this, the simple mechanism that we get into a derivative pricing is, we will try to establish a fair price for the derivative, right. We'll try to establish the fair price for the derivative using the equivalent Martingale measure, and based on that we will try to identify a replicating strategy, assuming that this particular derivative can be replicated, assuming that it is a complete market. We will try to build a replicating strategy, and we'll have to try to establish that this particular strategy is self-financing, which would lead to finding out the value of the derivative. So if this is the typical process, I have to first of all understand all these terms. What is meant by my replicating portfolio? So this is where we are trying to drive. Okay, now I am investing some phi t in some stock which is having a price of st. I am investing psi t in cash bonds, which are typically giving me a risk-free kind of a rate of return, or currently having a price of bt. So my value of the portfolio, the replicating whatever I am saying. So at this point I am investing phi t in phi t shares which are having a share price of st, and psi t bonds which are having a value of bt. So this becomes the value of my portfolio, correct? To which should replicate the payoff of that particular derivative. And I know this phi t and psi t because they are previsible processes. And now what we are saying is, let's say I want to talk about the gain in a small period of time, t plus delta t. So this is coming out purely like, okay, I have phi t shares. This has gone to st plus delta t minus st, plus I have psi t bonds where the price has gone to bt plus delta t minus bt. So it's as good as phi t times dst plus psi t times dbt. So if I'm looking at a pure investment gain, that pure investment gain is coming out to the phi t number of shares times the dst, which is that minute change in the stock price, and psi t times the dbt, which is the minute change in the price of the bond. So here is where we are trying to bring in a definition called self-financing portfolio strategy. I want to create a portfolio which is self-financing. So the moment if I am seeing that the value, right, the value of the portfolio is purely equal to the investment gain. If it is purely equal to the investment gain this much, we call that kind of a portfolio as a self-financing. So whatever the change in the value of the portfolio here, if it is equal purely to this investment gain, we call this kind of a portfolio as self-financing. Because at time t plus delta t or t plus dt, I don't need any kind of additional inflow or outflow to make the portfolio back equivalent to this much. So these two should be equal, right? I mean this minus v of t should, which is the dvt, it should be exactly equivalent to this. Then we are calling this kind of a portfolio is self-financing. So the required change in the value of a portfolio is equal to the pure investment gain. That is when we call the portfolio to be a self-financing kind of a portfolio. And when I'm using another word, a replicating strategy, right? All these things we actually do in a typical binomial pricing model. When I'm talking about a replicating strategy, I'm having a self-financing strategy in such a way that even at time period t, which is greater than t, the current time at a future date, all I am saying is the number of shares you hold at that point multiplied by the stock price at that point plus number of bonds you hold at that point multiplied by bond value at that point should be equivalent to the value of the derivative, what the derivative would give the payoff at that particular point. So a portfolio will be able to reproduce the derivative payment at time t without any additional risk and without any additional cost. And this is where the definition of the complete market also comes into picture. In case in any market I am having the securities in such a way that whatever the derivative payoff at different points in time is, there is a replicating strategy phi t psi t, which can be used to replicate these kind of payoffs at time t. And so this definition of the complete market is very comfortably be achieved or is very comfortably represented by the binomial model in the discrete case, and the log normal model for stock prices, even that is representing the same in the continuous time case. So these will form the important inputs as a part of doing the pricing of the derivative securities in the discrete as well as continuous time. And along with that, we also need to have an understanding of the equivalent measures, especially with respect to the probability measures. When I am talking about two measures P and Q, all we are saying is if they are equivalent, if I say that there is some positive probability of E occurring, then some event E occurring under the probability measure P, then it should be the case that even in the Q there should be some positive probability of occurrence for the same. Right? So, I mean, it may be, the value could be different. It could be 0.2 here, 0.3 here. But the moment if I am saying the probability that occurrence of an event E is positive under the P measure, I should also see that the probability of occurrence of that same event is positive even under the Q measure and vice versa. So that is when we talk about these two measures of probability being equivalent, right? And this is what will drive us to a very important theorem called CMG theorem, or in detail being called as Cameron-Martin-Girsanov's theorem. Let's look at what that theorem talk about. So what does this CMG theorem say? Here, let's look at Zt, which is a standard Brownian motion under the real world probability measure P. Now, it says that I can have an equivalent process, let's say Zt bar, wherein this is equivalent to Zt plus the integral between 0 to t gamma s ds. So this, wherein this gamma s for me is a pre-visible process, or gamma t for me is a pre-visible process, means it is ft minus measurable. It's a pre-visible process. Then what we are saying is a measure q equivalent to p exists in such a way that zt equal to zt bar is equal to zt plus the integration between 0 to t gamma s ds is a standard Brownian motion under the risk neutral probability measure q. So just this again reiterated in a slightly different way gives us the converse of this Cameron Martin Girsanov's theorem, which says, okay, Zt is a standard Brownian motion under the probability measure P, and if I know that Q is equivalent to P, then I'm sure that there exists a pre-visible process Zt there exists a pre-visible process gamma t in such a way that the zt bar is equal to zt plus integral 0 to t gamma s ds becomes a standard Brownian motion under the risk neutral probability measure q, which is clearly giving us that by doing this, by adding up this integral, I can make this, there is an equivalent standard Brownian motion that is getting created under a probability measure Q. I can change from a probability measure P by doing this integration, which is again clearly saying that the drift of the Brownian motion can be changed. The drift of the Brownian motion can be changed by changing the probability measure from P to Q or Q to P. If I am moving, I can change the drift of the probability measure, but in this case the volatility is not changing, only the drift, because this is a pre-visible process, this is going to be a part of the constant. So I can very well change the drift of the probability measure, but the volatility will remain constant. So we can very well change the drift and can very well create equivalent measure under the different probability measure. Now, just using this CMG theorem, let's try to look at, for example, now if I start looking at probability P is a real world probability measure, and Q, let me take it as a risk neutral probability measure, and I have gamma T, which is a pre-visible process as per the CMG theorem. And as per the CMG theorem, we have simply said that Zt, if it is a standard Brownian motion under P, I'm saying Zt bar, which is equivalent to Zt plus integral 0 to t gamma s ds, is also a standard Brownian motion under the risk neutral probability measure Q. Now, what should be the typical gamma s? Now, here if I have to go a little bit more deeper, if I want to know what is my gamma t for a non-dividend paying share, in regular case, non-dividend paying share, if I am taking The gamma t is nothing but mu minus r by sigma times t. The gamma t will become mu minus r by sigma times t, which is equivalent to market price of risk. Because this is the return which the security is giving minus the risk-free rate of return divided by the standard deviation, which is directly telling me that this is the market price of risk. Even if I am looking at the total, even for a dividend paying share, right? If I am looking at the dividend paying share also, the gamma t as a process comes out as mu plus q. This is the return plus the dividend, continuous dividend minus r by sigma times t, which is also equivalent to the market price of risk only. So once I know, I have to compute the pre-visible process in this mechanism where I am looking at mu minus r divided by sigma times t. So just by giving that kind of a change, I can very well, this is the change at drift as per the application of the Cameron Martin Girsanov's theorem, right? So that's the kind of an application that we can bring out from the CMG theorem, wherein we can try to find out the what is the pre-visible process in both in both the case of non-dividend paying share as well as the dividend paying share. Now the next important theorem that we may have to look at before we get into the deriving of the pricing model is the Martingale representation theorem. Martingale representation theorem in a continuous time, which is clearly saying, now let me think of a process xt, which is a martingale, right? Xt is a process which is a martingale under the real world probability measure p, which means the expected value of xt given the filtration up to time s is same as the value of xs. That is what we are calling as the martingale, and this is the martingale under the real world probability measure. Now if I also say that there is one more process yt which is also a martingale under the same real world probability measure, which means the expected value of yt given fs is same as ys. Now this is another kind of a important theorem that says there is a unique previsible process phi t. In this case, we see a unique previsible process phi t such that I can establish yt in terms of xt. I can write it as yt is equal to y0 plus integrating it between 0 to t phi s times dxs. Right? By doing this, I can convert, I can express one process in terms of the other in case it is a martingale. Means the expected value of this remains constant, the expected value of this remains constant. So we are trying to establish the one process in terms of the other process, or in a way the change in the y's is same as some phi t times the change in the x. This is a very interesting kind of an expression which we would be using as a part of our pricing of the derivative. So this kind of an expression exists if there is no other measure equivalent to p under which xt is a martingale. Only with this measure, if it is available and no other measure equivalent to p under which xt is a martingale that is available, this is the kind of a relationship that we are talking of. Now from that perspective, if I am seeing, okay, let's assume that at t plus 1 the price of xt is like xt plus u xt plus u, some with some kind of a probability of q, and it becomes xt plus d with a probability 1 minus q. Similarly, I look at one more process y. At t plus 1, it is yt plus some u cap, right, with some other increment again with a probability q, and yt plus some d cap with a probability 1 minus q. Now, if I have to look out for a Martingale representation theorem, now if I know that xt and yt are martingales, look at this. If they are martingale, the expected value should be the same, right? If these two are martingale, the expected value at t plus 1 should be the same as expected value of t, which means if I subtract whatever is the expected value of t, so it should be equivalent to xt. So which means q times xt plus u plus 1 minus q times xt plus d should be equivalent to xt only. So basically, if I am simplifying this, qxt minus qxt will go off. So this is coming out to qu plus xt plus minus qd should be equal to 0, right? So it's this is equivalent to xt, so which is also saying qu plus 1 minus qd should be equal to 0. The same logic, if I am saying with respect to y is also a martingale, even then I am getting qu plus 1 minus q d cap should be equal to 0. Now based on this, I can very well find out my d. Right from here I can try finding out my d minus qu divided by 1 minus q. Similarly, I can find out my d cap minus qu cap divided by 1 minus q. Similarly, if I am doing d cap by d, which is also coming out as u cap by u. And so here we are seeing that this equivalence has to establish, and we know that the increment delta yt plus 1 divided by delta xt plus 1 should be the same, because the increment d cap by u cap should be the same as d by u. So the increment and the decrement should be the same, which means whatever is the change at time period t, it is 5 times the change in x. So this is where, if this is a constant, we are calling that it's a previsible process. Phi t is a previsible process. It is known in advance itself. This is what is typically coming out with respect to the Martingale representation theorem. Now all these concepts will become some of the important things for us to go further in terms of finding out the value of a derivative security in a discrete time. Only when all these definitions are clear enough, using all these definitions, we'll try to do the pricing of the derivative security in discrete time. Right? So let's get started into the different steps involved in the pricing of the derivative security using all these concepts. All right. Now let's move towards identifying how do I do the pricing of a derivative. The general measures, probably the 5 steps which we do is, First of all, from the real world probability measure or otherwise, try first of all establishing an equivalent martingale measure Q. Right? Establish an equivalent martingale measure Q. Then the second step involves, okay, whatever is the derivative, right, which is paying different payoffs under different scenarios at a future date, whatever may be the payoffs, first of all, establish some kind of a fair price for it based on this equivalent martingale measure. Come out with the fair price of the derivative. Now on the other side, come out using the Martingale representation theorem, establish a replicating strategy, because you can establish one in terms of the other going with a Martingale representation theorem, especially if especially if there are two processes which are martingales. So you can come out with a replicating strategy. And make sure that that replicating strategy is not costly. The replicating strategy has to be a self-financing kind of a strategy, because it should not involve any kind of additional cash inflows or outflows. So, and it has to replicate the payoff of the derivative at time n, and it should have the value equivalent at Vt at time t. If that's the case, we can very well say that Vt, whatever we have established as the fair price of the derivative, will be the value of the derivative at time t. So this is what is a typical mechanism. Probably this is what we do in a binomial model based option pricing also. But in general, if I have to see, first of all, I have to come out with the equivalent martingale measure. Right, we are coming out with an equivalent martingale measure Q, where whatever is the asset price, if I want to find out the present value of it, I am discounting it by e to the power of minus RT times ST. I have to establish dt in such a way that this is a martingale under Q. This, is it a martingale under Q? Which means the expectation of dt given fs should be equal to expectation of ds. Right? So this is what will establish that it is a martingale under Q. Now once I have established that dt is this is a martingale, we can very well define, let's say there is a derivative that is paying C1, C2, C3 with some kind of probabilities at time 1, C2 at time 2, C3 at time 3, Cn at time n. Right? So probably different kinds of payoffs being happening. So I can very well find out the expected value of Cn given Ft. Right, I can find out the expected value of Cn given Ft under the Q type measure, discounting it to the present value R times n minus t. So this is a martingale anyhow, because this we said is a martingale, whatever is the price of the asset and expected price of the asset, I am coming it to the present value. So this is what I am initially defining as the price of the derivative security. Now, so if at all the derivative is paying some amount Vt at time period t, the expected value at the current is e power minus RT times Vt, and obviously we know that this is a martingale. And once we know that this is a martingale, I have established it, I can very well find out what is the phi, how many, let's say I'm creating a kind of a replicating strategy where I'm investing phi t in the stock and psi t in the bonds, wherein the same payoff is replicated at time t. I can very well find out what is the value of phi t as well as psi t, and based on that I'm trying to find out the value of Vt. A very easier way of this can be understood if we are going with the binomial tree based measure, which is doing the same stuff. If I have to go with the same stuff, okay, let's assume that the current stock price is S0. I assume that it can go to S0 times U with some probability Q, the risk neutral probability measure, and there is 1 minus q probability that it can go to S naught d. And let's say I have a derivative that is paying Cu if the price is going up, and that will pay Cd if the price is going down. Now what we are saying, let's say at time 0, I am having 5 units of stock where the price of it is S0, and psi units of cash which I am having at this moment, which means the total worth of my portfolio today is this much. Now what is that we are saying, at in case the stock price goes up, right? In case the stock price goes up, if I see that I am having 5 number of shares, the price of that will go to psi S naught U. And at the same time, because I have psi cash, and because of the risk-free rate of return, it is going to give me this much. So my value of my portfolio is going to become this much at the time U, at the time 1. Similarly, if it is going to go down, if the price goes down, the value of my portfolio is becoming phi S naught D plus psi times e power r. So when it goes up, it's going to be this. When it goes down, this is going to be this. Now, even my derivative, if the stock price is going up, it's ready to pay me Cu. If it is going down, it's ready to pay me Cd. So what is that I'm saying? Now from here, I can very well find out my phi. S naught U minus S naught D is equal to Cu minus Cd. Or phi, which is the number of shares I have to purchase, is coming out to Cu minus Cd divided by S naught into U minus D. Similarly, if I have to find my psi, phi is Cu minus Cd divided by S naught into U minus D times S naught times U plus psi e power r is equal to Cu. Now here I can take this out, which works out to me that psi is Cu minus UCU minus of UCU minus UCD divided by U minus D, and this entire thing e to the power of minus r. So it gets simplified, e to the power of minus r into UCU minus DCU minus UCU plus UCD divided by U minus D. So these two, if I am taking out, it's working out as e to the power of minus r times UCD minus DCU divided by U minus D. Mean I'm able to create a portfolio with 5 number of shares, which is equivalent to Cu minus Cd by S naught into U minus D, and psi number of units in the bond, which is equivalent to e power minus r times UCD minus DCU by U minus D. right? So this is what is the value, I mean, this is what is the replicating portfolio for me. Now, what is that I am saying? The value of that portfolio. Now, we know that there is a Q probability that it is going to go up. There is a 1 minus Q probability that it is going to go down. From here, I can say Q times S naught U plus 1 minus q times, if I have to establish q as a risk neutral probability, 1 minus q times s naught d should be same as s naught into e power r. So from here I am getting q is nothing but e power r minus d by u minus d. This is the risk neutral probability of going up or going down. Now, if I know that this is the kind of a replicating portfolio, I'm seeing what is the value of it, 5 times S naught. So, which means Cu minus Cd by U minus D plus psi times e power minus R times UCD minus DCU by U minus D. Now probably, yeah, this is an interesting piece. So let me express it. Right, the value of the portfolio right now is coming out as Cu minus Cd by U minus D plus e power minus R times UCD minus DCU by U minus D. Now I can bring the like terms together, right? Now we have got on the other side the risk neutral, it came out as e power r minus d by u minus d. So let me try that kind of expression here. So let me take all this cu minus e power minus r dcu by u minus d plus or minus cd minus e power minus r ucd by u minus d. Now overall let me take out e power minus r out, right? So here, okay, let me try out if I am saying cu, if I am taking out this part, it, and probably let me take e power minus r also out. So let me take from this e power minus r times cu out, which comes out like e power r minus d by u minus d, minus here also let me take e power minus r times cd. This works out as e power r minus u by u minus d. Now, if I am saying e power r minus d by u minus d is some q, right? What is 1 minus q then? 1 minus of e power r minus d by u minus d. This will become u minus d minus e power r plus d by u minus d. So, u minus e power r by u minus d will become 1 minus q. So basically it is becoming e power minus r cu, and if I say that this is q, then minus e power minus r cd e power minus r minus mu, it is becoming minus 1 minus q. So probably now this gets simplified. E power minus r, if I take out, it is becoming qcu plus 1 minus q times cd. So that is where this entire thing, the present value of the portfolio is directly coming out as the risk neutral probability, the risk neutral probability of the derivative payoff when the price goes up. So this is nothing but it's an expected value of the derivative. right? The expected value of the derivative, I'm finding out the present value of that, which is what is giving me the value of the derivative. So this is what typically goes as a part of the finding the present value of the derivative security of any kind of a derivative, which means I'm trying to find out the futuristic, I'm trying to find out all the payoffs of the derivative, trying to see if I'm trying to replicate a portfolio which is a self-financing kind of a portfolio, and using that trying to find out the value of the derivative security. Probably this understood, the whole process is very comfortable, right?